Have you ever heard the claim that we only use 10% of our brains? Neuroscientists argue that this isn't true at all. We actually use every part of our brain. Yet, not everyone utilizes their brain equally efficiently. Depending on one's lifestyle, habits, and learning experiences, some people spark incredibly creative ideas and devise brilliant solutions, while others find themselves stuck in cliched, inefficient thought patterns. Geniuses often achieve feats that most of us can hardly fathom. Is it simply that they are born with an innate knack for brain power? While talent certainly plays a role, it isn't the whole story. In fact, many great minds share certain lifestyle patterns when they make their groundbreaking discoveries. If we could emulate even a bit of that, we might be able to unlock far more of our brain's potential. The ideas I'm about to share are based on the book The Primacy of Doubt. Its author, Tim Palmer, is a physics professor at Oxford University, a student of Nobel laureate Roger Penrose, and a brilliant scholar whose work was pivotal in developing the modern weather forecasting systems we rely on today. Palmer explains the universe through chaos theory, suggesting that our brains, too, have chaotic elements, and that harnessing this chaos can unleash peak efficiency. This isn't your run-of-the-mill self-help advice. It's a profound hypothesis rooted in both science and philosophy. To grasp Palmer's argument, we first need to appreciate the importance of randomness or noise. Consider how you might calculate the area of a circle. In math class, you probably learned the formula pi r squared. Since we already know how much is pi, we just need to measure the radius, square it, and multiply. It's a neat, orderly process. Now imagine an alternative, rather unconventional method. Draw a square around the circle, then randomly scatter points over the square. By counting how many points fall inside the circle and comparing that to the total number of points, you can estimate the circle's area relative to the square. For example, if the square side is 20 and out of 400 random points, 314 land inside the circle, then the circle's area is roughly 314. The more points you scatter, the more accurate your estimation becomes. Even without knowing how much is pi, you can probabilistically approximate the circle's area. This method may seem chaotic and messy compared to the clean pi r squared formula calculation, yet it gets us to our goal. This ingenious use of randomness finds practical applications in numerous fields. One striking example Palmer offers is the transmission of visual data. Imagine sending a computer image composed of various shades of gray, each text representing a percentage of black. An image with 85% black appears almost pitch black, while one with just 15% black looks nearly white. These images are made up of very large amount of pixels. Now, suppose you need to transmit this image, but due to bandwidth constraints, you can only send a binary version. Each pixel must be either black or white. If you were to simply round off based on the original percentage, any character with over 50% black would become entirely black, and those under 50% would be entirely white, resulting in a significant loss of detail. The solution? Introduce random noise. For example, for a pixel originally at 30% black, generate a random number between 1 and 0 for each pixel. If the number is less than 0.3, set the pixel to black. If it's higher, set it to white. With a significant large amount of pixels, roughly 30% will be black and the rest white, preserving the nuance of a light gray image. Repeat this process for every image, and while the outcome isn't perfect, it's impressively effective. This example offers a powerful insight. In an ideal world with unlimited computing power and energy, we could finally mix black and white at every pixel to create perfectly accurate images. However, real-world hardware always has limitations. When forced to compress data into a binary choice, much information can be lost. But by introducing a touch of randomness instead of an all-or-nothing decision, we can preserve a recognizable form of the original image. Another example, imagine you have to remove 50% of the pieces from a jigsaw puzzle. If you simply draw a neat line and remove exactly half of the overall picture becomes completely unrecognizable. However, if you randomly remove 50% of the pieces, you can still make out the overall outline of the image. Now, let's circle back to our brains. The human brain is a marvel, operating on roughly 20 watts of power, astonishingly low compared to supercomputers that gulp down over 20 million watts. Yet, our brains perform incredibly sophisticated tasks with this minimal energy. Sometimes they achieve what even the most powerful computers cannot. Psychologist Daniel Kahneman describes the brain's operation as divided between System 1 and System 2. System 1 is on almost every time, handling multiple tasks at once without much conscious effort, like watching a YouTube video while eating or walking and checking your phone, favoring rough approximation over detailed analysis. In contrast, System 2 is the focused mode that kicks in when solving a challenging problem. It might involve shutting out the world, closing your eyes, or even blocking your ears to concentrate fully. Interestingly, both systems consume similar amounts of energy overall. The difference is that System 1 spreads its energy across many tasks, whereas System 2 uses it more intensively on one. Yet, some of the most groundbreaking ideas from geniuses emerge not from System 2, but when they are in System 1 mode. Legendary mathematician Henri Poincaré once had a revolutionary insight while traveling between cities, and Nobel laureate Roger Penrose experienced a decisive moment of inspiration while pausing his conversation at a crosswalk. Among the 20th century's brightest minds, mathematician Andrew Wiles remarked, "To generate a truly new idea, you must dive deep into the problem without distractions, as if it were the only thing in the world. Then, when you finally take a break, a kind of relaxation sets in, and that's when the breakthrough occurs." All these great minds reached their most innovative moments while their brains were in a more relaxed System 1 state. When energy isn't overly concentrated, the brain becomes more susceptible to noise, which paradoxically can reveal patterns that a strictly orderly approach might miss. Palmer hypothesizes that this noise, linked to electrical voltage in our neurons, allows our brains to piece together the big picture. Just as computer transistors can generate random signals if the voltage is low, our neurons, of which there are over 80 billion, can produce spontaneous signals when their voltage wanes. Although this might seem like a recipe for error when looking at a single signal, the sheer volume of signals traversing our brain means that this randomness can evolve into a coherent, innovative idea. So when does our neural voltage drop? Although our overall energy remains around 20 watts, during System 1 mode, the energy allocated to any single task diminishes. This is when neurons become more vulnerable to noise, and it's precisely at this moment that we begin to notice ideas that would remain hidden in a purely orderly signal. Palmer even extends his argument with an evolutionary twist. Smaller diameter neurons are more susceptible to noise and have slower signal speeds, which in situations requiring rapid responses to predators might have been a disadvantage. However, as humans evolved into social creatures, quick reflexes became less critical for survival. Instead, developing numerous fine neurons that harness noise synergistically may have enhanced our capacity for innovative thinking, giving us an evolutionary edge over rigid, strictly rule-based algorithms. In conclusion, to maximize brain's potential, we need to take breaks. It's not about over-focusing on one task all the time. Sometimes a little mental wandering is exactly what's needed. That said, System 2 remains crucial. Even if a fantastic idea emerges during a break, it must be rigorously tested with focused effort to ensure it holds up in the real world. The stories of geniuses aren't about sudden flashes of brilliance in isolation. They're about diving deeply into a problem, absorbing every detail, and then letting a bit of chaos in to spark innovation. So rather than simply taking this video as a cue to slack off, let's commit to working hard, interspersing our intense focus with well-timed breaks that allow those innovative sparks to fly.